change this. Wait, why? What's going on? Wait, oh. Oh. You guys see this? Okay, I think it's time to start. So hopefully everyone has a good holiday. Any question from this time? This time we go over this linear independence, and today we are going to talk about basis and dimension finally. Well, this is a big reason why we want to talk about linear independence. And yeah, but let's have a quick review about this time. So this time we talk about this concept of linear independence. So I guess before linear independent, we have linear dependent. Linear dependent idea is that some vectors are linear dependent if one of them can be written as a linear combination of others. Okay, so say there's some Vn that can be written as a linear combination of V1 to Vn minus 1. And why we care about it is because if Vn can be written as a linear combination of others, then the span of V1 to Vn is same as the span of V1 to Vn minus 1, because you can write the Cn Vn as other things. Okay. Where do we have that? We should have. Yeah. Wait. This is weird. Okay. Anyway. Oh, you're weird. Anyway, so that's the idea of linear dependence. So one of them can be written as a linear combination of others, and we prove that the linear dependence or independence, and so if that's possible as a linear dependent, if that's impossible, then that's linear independent. And we show in this summarization that we have a good mathematical form to say it. That is, we check this formula. So C1V1 plus C2V2 plus all the way to CNVN, where when it's equal to 0 vector, what about what are the possible solution to this scalars C1 to Cn? So these always has the trivial solutions, they all equal to 0. And if V1 to Vn are linear independent, then then the solution to this equation is all the C equals 0. But if they have non-trivial solution, yeah, if it has non-trivial solution, then then those vectors are linearly dependent. Okay. And so we just use this C1V1 to CNVN equation as a definition for linear independent and linear dependent. So once again, the vector V1 to Vn is linear independent if this equation only has a trivial solution, C1 to Cn all equal to 0. And it has and those vectors are linear dependent if this has a non-trivial solution. So some of the C's are not equal to 0. Okay? And we are going to see today that if it is linear dependent, then we can keep eliminating the vectors to get a minimal spanning set, and so we can keep eliminating them until they are linearly independent, and they'll become a basis of your vector space. Okay, that's a little later today, but let's keep the review. Yeah. So we have some vectors and we want to check whether they are, okay, so now we have some vectors and we want to check whether they are linearly independent or linear dependent. So we write, okay, so brute force basically check this. We want to check this equation whether it has solution or not. And so if we write it very generally, right? So I want to check this equation whether it has a non-trivial solution. Okay, and so here is some geometric interpretation. So linear dependent of two vectors, it looks like this. They are on the same line and linear independent, then they are not on the same line. So they actually span the plane instead of just spanning a line. Okay, so you can see linear dependent is kind of singular case. Okay, and in three vectors, 3 dimension, linear dependent means all three in the same plane, etc. And linear dependent you can stick out. And now we have vectors and we want to check whether they are linear independent. And so basically we check this formula. We check this formula whether it is equal to 0. And we find out that it's basically a linear system of equations for those C's. So we have C1, C2, C3 here. And we write it out and you see that it's this linear equation of C's. And so it's basically, well, linear system equation, then we always write it as this xc equal to 0, right? We have a linear system equation, then we can put all the coefficients into some matrix big X. And then we see that this big X is just formed by the vectors. So then we have vectors that we want to check whether they are linear independent. And we think they are the column vectors. And so when we write down this equation, C1, Ci, Xi, summation equal to 0, then we see its form, then we see that it's same as the xc vector equal to 0, where c vector is this vector of C1, C2, Cn, and x is the matrix formed by having columns as those vectors. Okay, so columns are x1, x2 to xn. Okay, so whether xc equal to 0, and well, whether xc equal to 0 has a non-trivial solution from previous chapter. So when we talk about determinant, we see that we have a very good way to characterize this when big X is a square matrix. That is, we just need to check whether X is singular, right? I guess it's in chapter 1 we prove this. So this thing has a non-trivial solution if only if X is singular. Okay, and that means these vectors are linearly dependent if and only if X is singular. And we also know X is singular if only if determinant X equal to 0. Okay, so we can just calculate the determinant of X and to see whether the vectors are linearly dependent or not. So determinant of X equals 0, then the vectors are linearly dependent, and the determinant of X not equal to 0, then the vectors are linearly independent. Okay, and so here we can calculate this this example. So we calculate the determinant if one is 0, and the vectors are linearly dependent. Okay, and I guess that's all we had from last time. So any question yet about linear independent and linear dependent? Yeah. Yeah. So I guess once again the intuition. It's good to have some intuition about this. The intuition about this is so linear independent vectors. Each one of them has stick out in some other dimension. Okay. So when you consider span, each one of them is contributing to span in a bigger space, and none of them can be written as just combination of others. Okay, so it has some extra dimension. So for example, this z vector, it has some component in perpendicular to this xy plane. So so it's linear independent to x and y. Okay, okay, but that's some vague intuition that we won't make formal yet, but hopefully I'll give you some idea. Anyway, so that's linear dependent and linear independent, and we have some vectors. Want to check whether they are linear independent or not. Then we want to check if this equation whether it has non-trivial solution. And if X is a square matrix, we can check the determinant. But okay, so now something new. So once again, we have k vectors. So now we have k not equal to n. So now we have k vector x1 to xk, and let's say the n-dimensional vector in some Rn. And we want to check whether c1x1 plus want to check whether linear independence. We want to check whether this equation is a non-trivial solution. And still we can do the matrix. Not quite manipulation, we just rewritten things in other form, and we see that this is saying us whether the linear system big xc equal to 0. Okay. Where x is this big matrix formed by just put the columns side by side. So the first column of big X is x1 vector, second column is x2 vector, etc. All the way to k's column. And now the quadrant is if we don't have a square matrix, so k not equal to n. And then how do we decide whether this system has a non-trivial solution? Because there is no determinant for non-square matrix. Okay. And anyway, there is always a trivial solution. System is homogeneous, so corresponding to all the c equal to 0, then obviously this is a solution to big X c equal to 0. Okay. And okay, so if we cannot do determinant, then we do something that's basically how you calculate determinant. That is, we need to go back to doing the Gaussian eliminations. Okay, so if you cannot calculate the determinant, then you just do Gaussian elimination to get x equal to row echelon form. That's how we solve linear system, right? Where in chapter 1 we say we have a linear system, we'll solve it. Then we do the row operations to make it into this row echelon form. Okay. And once in row echelon form, then you can get a good idea about the the solutions of x, because if you have a free variable, then you know you have a non-trivial solution. Okay. And yeah, so that's what you do. You do Gaussian elimination to put the x equal to row echelon form. And if you have free variable, then the system is linearly dependent because you have non-trivial solution. And if you have no free variable, then you know that you have you only have the c equal to 0 solution. And so the system is linearly independent. Okay. Okay. And so here we can get a small corollary that we will see more general later. Right? So in what case we always have free variable, that is if we have k more than n, right? So if our matrix look like this, okay. So if a k longer than n, then the row echelon form, the most you can do is you have 1, 1, 1, 1 here, right? And then you still have a lot of free variable here. So those are free variable. Okay. So you see if k more than n, then you cannot make every row pivot, and so not every column pivot. And yeah, so you have some free variable around, and you will be linearly dependent. And we'll see this in more general, hopefully later part today. Okay, and let's see an example. Okay, but this is not a k bigger than n example. This is 4 dimension, and we want to have 3 vectors, and we want to see where they are linearly dependent. Okay, and yeah, so if you just want, and yeah. So we write this solution. So we try to solve, once again, we try to solve this x equal to 0. And so x, as we say, is you list those vectors together to form a matrix, big matrix x. So x1 here, x2 here, x3 here. And then we do Gaussian elimination. Hopefully we've done a lot of those in chapter 1. So we do Gaussian elimination. So you eliminate the first column, make those all 0. and then you can make a second column also 0, and we see that we are in a very singular case. So yeah, so we see we got a lot of 0 here. Okay. And but those are not super important here. What's important is here. So we want to check whether there are free variable, and there are indeed free variable. Okay. So we see that this column is a free variable because it got 0 here. So if it's not free variable, then we'll have a 1 here, right? And yeah, maybe a circle here. Yeah, because we got lucky that when we eliminate this row, this column also eliminate this column. So we got a 0 here, and this makes the third column free variable. And because we have free variable, then we know that there is a non-trivial solution to x equal to 0, and those three are linearly dependent. Okay? Any question? This goes all the way to chapter 1. And this is a general formula that's basically when you want to solve anything in linear algebra, it always go back to, I guess it's not always, but a lot of time it goes back to doing Gaussian elimination. Gaussian elimination is a very efficient and useful process in doing linear algebra. Okay. Okay, and I guess we can probably have time. I can say a little more, and so one thing funny to see here is that so we say that we want to do different things for k not equal to n because we cannot calculate determinant. But we see that what we do is we do Gaussian elimination. And if you remember, we say that one pretty efficient way to calculate determinant is also doing Gaussian elimination. So you see that whether k equal to n or not is kind of similar. In the end, in the end, you want to do Gaussian elimination to calculate something. Yeah. And yeah, so this is an example of Gaussian elimination being very useful. And now I'm a little slow. Okay, hopefully we still are on schedule. So yeah, so let's theorem about linear independent, and this is actually a little more useful when we know basis. But for now, let's just talk about this in linear independent. So we have vectors in vector space, and well, the vectors span something. Okay, so everything inside them, well. By definition of this span, everything that is span can be written as a linear combination of those vectors. Okay? That's a span. But if vectors are also linearly independent, then this return everything inside span as a linear combination of v1 to vn. They are special because the linear combination is unique. Okay? And this is a if only if equation. So. But I guess if one is one people like more because that means it's a basis. Spoiler a little bit. So it's so if you consider span of those vectors, and if those vectors are also linearly independent, then we say it's a basis for this span. And anyway, but for now, let's just prove this theorem. So so we have that it's linear independent, and linear combination is unique, and also if it's unique, then the linear combination, if the linear combination is unique, then those vectors are linearly independent. Okay. Okay, and so let's see the proof. Yeah, and I guess the first is we prove that if one, which I say is more important in some sense. Yeah, so if you are v1 to vn is linear independent, and we consider some v that's in span of those vectors, and we say it can be written as a linear combination of some of them. And now we kind of go to the contradiction proof. I guess not quite, but anyway, so v can be written as a linear combination of v1 to vn, as given, okay, so with some coefficient alpha 1 to alpha n. And what we want to say is those alpha 1 to alpha n, they are all unique. And so we assume it can be written as something else, so beta 1 to beta n. Okay? And let's see that this beta 1 to beta n must equal to alpha 1 to alpha n. And what we do is we subtract those two equations. And so v minus v will become 0. And well, then those coefficients, they will just subtract each other by the linearity. So alpha 1 minus beta 1, alpha 2 minus beta 2, etc. Okay. And then now we use the linear independence, because now we actually get the equation of, so we can view those alpha 1 minus beta 1 as c, right? So we have c1 v1 plus c2 v2 all the way to cn vn equal to 0. And then that's exactly our equation of the definition of linearly independent, right? So c1 v1 c2 v2 to cn vn equal to 0. Then because they are linearly independent, all those c must equal to 0. C equal to 0, then that means alpha 1 equal to beta 1, alpha 2 equal to beta 2, etc. Okay. And yeah, so that proves that if all those v's are linearly independent, then the linear combination of them is unique. Okay. So if some vector is a linear combination of it, then it cannot be another linear combination of it. Okay. So the linear combination is unique if the v's are linearly independent. And then we have other one. Okay. The other one we do now we actually do a negation proof. Okay, so it's we are saying if it's unique, then it's linearly independent. And so we do the contrapositive. We say if they are linearly dependent, then it must be not unique. Okay, and yeah, so if they are linearly dependent, then then we back to our definition of linear dependence. So we say we have a non-trivial solution to this 0 equal to c1 v1 plus c2 v2 to cn vn. And yeah, so we basically do reverse of this. So we say some v is some linear combination alpha 1 v1 to alpha n vn. Then we can add a 0 vector to it. Okay? So v plus 0 is still 0. And and the other side we have alpha 1 plus c1 v and alpha 2 plus c2 v all the way to alpha n plus cn v. And and those alpha plus c, we call them beta. And because it's linear dependent, so those c's are non-trivial, and so there must be, so there is some c not equal to 0. And so there must be some beta not equal to alpha. Okay, so yeah, so we prove that if they are linear dependent, then there must be, then the then the expression of v as a linear combination of v's are not unique. Okay, and yeah, this is what we had to say. Okay. So that's 3.3. So once again, linear independence and linear dependence is defined by this equation, where c1 v1 to cn vn equals 0 has non-trivial c as a solution. And okay, so we're a little short, so the checklist you can see then yourself later in the course. And let's go to the next slide. Let's go to actual basis, save, and 3.4. Oh, now this one is PDF. Okay, 3.4. We actually know basis, and okay, 3.4. Basis and dimension. And let's see, this 3.4, this one. Okay, should be good. Okay, yeah, everyone is still on page. So yeah, we now go to basis and dimension. So what is basis is crucially used linear independent. And we kind of already see this in 3.3, but here we have a formal definition. So, well, basis is defined for a vector space. So for vector space V, and basis is a set of vectors. And the set of vectors need to have two properties. So you need to span V, right? So V1 to Vn need to span V, and that means. I guess we can talk a little more. Let's talk about the definition first. So V1 to Vn need to span V, and also V1 to Vn need to be linearly independent. Okay, two things. So we basically for basis, although we won't do today, is we want to write for every V in V, we want to write V as alpha 1 V1 plus alpha 2 V2 plus to alpha n Vn. Okay. So what we want the basis is we want to write everything inside V as a linear combination of the basis vectors, and so that's why we want those two equations, those two conditions. Okay, because for the second condition, that means everything in V can be written as a linear combination, and the first condition we just proved that if we have this, then this linear combination is unique. Right? So all the alpha will be unique if they are linearly independent. Okay. But let's probably jump ahead a little bit. We won't actually talk about this. We'll use this basis idea to define dimension first. So we have been, I guess, smuggling the idea of dimension, right? Like we say we are in Rn, and we see this dimension n. But here we will define dimension for more abstract vector space. So say m times n, those matrices, what is the actual dimension, etc. Anyway, let's see some example of basis. So we have standard basis R3, and it's a good example of you want to see a linear combination, right? So standard basis of R3 is E1, E2, E3, and so you see that whatever vector ABC, alright, so you have some vector ABC, then it's like A, E1 plus B, E2 plus C, E3, etc. So that's standard basis. But anyway, let's check the definition. So E1, E2, E3, they span R3 because, well, we just say, and also they are linearly independent because none of them can be written as a linear combination of others. Okay, and but that's a standard basis. But you can also choose weird basis. Okay, so for example, this is a basis and this is a basis. You can check that. They span R3 and they are linear independent. Okay, and we are going to see this idea of dimension, that is R3 actually has 3 dimension, means that every basis has 3 elements. Okay. So that's first. So we want to say this dimension thing. So we'll have a lot of theorem to prove. Probably won't be able to finish today, but let's see. So first theorem is that if you have a spanning set for some vector space, so you okay. So if the vector space can be spanned by n vectors, okay, and there is another set of vectors that has n of them, then the n vectors must be linearly dependent. Okay. And so let's go to a proof first. So if the n vector already span V, then we have another n vectors. So we have those U1 to Un. They also span V. They don't need to span. So we have another n vectors. Then the n vectors must be linearly dependent. Okay. And so let's go proof. So proof is that, well, the vector v1 to vn already span v, and then we can write every u as a linear combination of v. So we have ui as ai1 v1 plus ai2 v2 all the way to ain and vn. Okay. And then we want to check a linear dependence, so we do this linear combination of it. Okay, so c1 u1 plus c2 u2 to cn vn un, and then we can read it as v. And okay, so there are too many summations, so we actually use a summation sign here. Okay. So it's c1 sum j a1 v j and c2 sum j a2 vj. So those sum is just you break the u equal linear combination of v's. Okay. And so yeah, so we write things in summation sign. So you have the sum I of those ci and the sum j of those aj vj. And as usual, we can change the order of summation sign. So you just put c inside, and hey, you put c inside, and you sum j first, you sum a. Okay. Okay. And then then we consider the middle part here, right? Okay. So want to see whether we have some non-trivial c to make this 0. Okay. And yeah, so I guess say a little. So we want to make this equal to 0. Okay. So if I can find non-trivial c to make this 0, then we show they are linear dependent. And I guess what we want to show is we can make every one of those 0. Okay. If we make every one of those 0, then yeah, then we have summation of 0 times every vj, and that will be 0. Okay. And yeah, so let's see how do we make every one of those 0. So for every j, we want to make this 0. Okay. So it's aij cj equals to 0. And but now we use okay, and we can written this as yeah, this is a little confusing. But so we can kind of think this as so we can write big A dagger, big A transpose. That's like some big A transpose. So we have C. So each one of them is AJI, and so we have AJI here, and we have vector CI here, and 1 equal to 0. We will write this as a linear system of equations. And okay, because we have I and J here, so AT is this here, is this matrix here, and so we can count the dimension here. Okay, so the number of unknown is m here, and let's see, yeah. So number of unknown is I, and that's n. Okay, so I should draw this longer. Sorry. And the number of equation is n here. Okay, and so we see we have more unknown than equations. And so by theorem 1.2.1 is really long ago. But basically, if you do Gaussian elimination of this thing, and you will see that because you have more variable than equation, you always got free variable. So you always get a non-trivial solution. So yeah, once again, we do our proof by doing Gaussian elimination. Okay. So you can always find non-trivial C so to make all those summation aij ci equal to 0. And yeah, that means you have all those c equal to 0. You have non-trivial solution to this c. We mark the non-trivial solution as c hat. And yeah, and so all the c hat u summation equal to 0. Yeah, and that means all those equal to 0, and that means the summation of those equal to 0. Okay, yeah, so yeah, all those things are 0, so you have summation of 0 times every v, and that's 0. And yeah, so finally we prove what we want to prove. We prove that if n vector already span your vector space, then you have n more than n vectors, then those vectors must be linearly dependent. And it goes back to Gaussian elimination and check the free variables. Okay. And okay, now we go to the interesting corollary. So we have two sets, v1 to vn and u1 to vn, u1 to un. And if they are both bases for vector space v, then n must equal to n. And that's why, because remember, basis means that they both span v and they both are linearly dependent. Sorry, linearly independent. Okay. And yeah, and just from the theorem we prove. Okay. And so we can do this just two ways. So because v1 to vn is a basis, right? So v1 to vn span v and span v, and from the theorem we just prove, then yeah, so both of them must span v and are linearly independent. And yeah, and so first we use v spans v, and those u's are linearly independent. And then from the previous theorem, then this n must be smaller or equal to n, because those already span v, so we know we can those linear independent things can have more than n vectors. And then we just go the other way around. Those things also span v, and those u's must also spanning v, and the v's are also linear independent. So n must be smaller or equal to n. And you want those both equations to be true, then n must equal to n. Okay. So we prove that every basis for the vector space must have same number of vectors. Okay. And the same number, we call it a dimension. Okay. And yeah, so finally we define the dimension of the vector space. It's the number of vectors in its basis. Okay. And so I guess in that prove that in Rn the dimension is n, because Rn always has a standard basis e1 to en, and so the dimension of Rn is n. And prove that well, every basis of Rn must have n vectors. Okay. And yeah, anyway, that's a very abstract way to define dimension, and it works for every abstract vector space. Vector space has dimension n if it has a basis of n vectors. And we prove here this corollary prove that the definition of the dimension is consistent, because every basis has the same number of vectors. Okay. And yeah, just stop a little bit. Any question about dimension? This is a very important concept. And anyway, so we have some interesting cases here. So the subspace, so we have this really weird subspace that is only a zero vector, and it's really spanned by nothing, and we just define its dimension v0. Okay, so it's like there's only one element, and we define it to have dimension 0. It's kind of a singular case to give it a special definition. And also if so we kind of assume that everything is finite dimensional. The basis we always write it as v1 to en with some finite n. So those are said to be finite dimensional if the set of if the basis has a finite number of vectors. But there are also infinite dimensional vector space where the basis consists of infinite number of vectors. They are a little weirder and we mostly avoid in this course. Although in the book we actually talk about infinite dimensional spaces, like the space of polynomials, etc. But we didn't have the example in the slide, so that's nothing too much about it. Yeah. Those are little more mathematical. So I guess in computer science we mostly deal with finite dimensional object. That's how you store in your computer. But infinite dimensional objects are really interesting. It's useful when you consider electrical engineering. But okay. Anyway, let's see some ideal basis. So if you consider a span of just one vector x, and then right, so x is linear independent of itself, and its span is on space, so this is span x, and it's now it's a one-dimensional subspace because you only span by one vector, okay, and it's a line. And then we consider two vectors in R3 x, y if they are linear independent, and they will span this plane, and we see the two-dimensional. And finally, if x, y, z or linear independent of each other, they will span whole R3, and it is three-dimensional. Okay, so this is some geometric intuition about the dimensions. So you see span over one basis element is one-dimensional, span over two elements, two-dimensional, and span over three elements is three-dimensional whole space. Okay. And okay, then we have two theorems to prove on those bases. Okay. So remember, bases are things that. Okay, so we have those three interesting things. Okay. So basis is set that span your vector space and is linear independent. Okay. And if it's its number is a dimension n. And we have this funny theorem 3.4.3 says that okay, so if your space already has this dimension, then actually any two of those conditions will give you the third one. Okay. And yeah, so two things. So you have linear independent vectors, and yeah, if you have linear independent vectors, and you have n of them, then they must be then they also span V, so it's a basis. And also if you have n vectors and they span V, then they must be linear independent, and that also means they are basis. Okay, so that's the proof of this. I think the proof is pretty illuminating to some of the ideas here. Okay. So yeah, first thing, if we have a linear independent and okay, so both of them we start with, we have well, it's not quite dimension, but we have n vectors. So n vectors and they are linear independent, and they want to say span V. So vectors, they are linear independent. Okay, want to say span V, so we want to say a vector in V can be written as a linear combination of them. Okay. And okay, and yeah, and we start with the vector space as dimension. And yeah, so any vector V want to say it's a linear combination, then so we consider oh, okay, I write this wrong. Okay, so we consider a set where we have V1 to Vn, and we also add V here. Okay, so we consider this set of n plus 1 vectors. Okay, V1 to Vn and V. Okay, and as the theorem we start this chapter with is theorem 3.4.1, right? And wait, sorry. Oh, okay. Then yeah, we kind of I guess it's from the corollary kind of. Okay. And so we know the okay. So here the logic is a little longer. So we know so here we use the dimension of V is dimension of V is n. Okay. Dimension of V is n, then that means that it has a basis of n vectors, and then that means it's n minus 1 vectors. So here we use dimension of V equal to n. And the dimension of V equal to n, and that means that those n plus 1 vectors must be linear dependent. Okay. Because, yeah. That's the first theorem of proof. If we have n vector already span V, then any n plus 1 vector must be linearly dependent. Okay. And that means that, so linear dependent, that means that you can write this equation with non-trivial solution. So C1V1 to all the way to Cn plus 1V, they sum to 0 with non-trivial solution. And then we particularly care about this Cn plus 1. Okay? Can it be 0? Okay? And we say it cannot be 0, otherwise those are not linearly independent. Okay? Because we start with V1 to Vn being linearly independent. If it's 0, then we have the C1 to Cn part has a non-trivial solution, but exactly contradicts the that this condition that they are linearly independent. And yeah, so the Cn plus 1 is not 0, then we can move things around to write V. So now we can divide everything by Cn plus 1. And yeah, so we can write V as a linear combination of V1 to Vn. And but we start with V as any vector in V. And so small v as any vector in the space big V. And so we see any vector can be a linear combination of V1 to Vn. And so yeah, so V1 to Vn actually span the whole space V. Okay. And question. Okay. Okay. And let's go through the other proof. So this is something we'll use to argue about a lot of things. Okay. So the second one is that you have n vectors, and they span V, then they must be linearly independent. Okay. And this is a process that a mental process we want to do a lot. So say our say our vectors V1 to Vn, they are linearly dependent. Okay. And so we want to find the So we want to find the minimal linearly independent set from it. And what we do is we say, is it linearly dependent, so there is some Vi, that's a linear combination of others. And let's say is I equal to n, because indexes doesn't really matter. So make our notation a little easier. Okay. So assume Vn is a linear combination of others. And so if we get rid of Vn from this set, then we have the V1 to Vn minus 1. And yeah, and from our discussion in 3.3, we know that this still spans V, right? And yeah, and now we can check again to see whether this is linearly dependent yet. If not, then we get rid of Vn plus minus 1, etc. All the way until we get V1 to Vk. Okay. Okay. And okay, so finally we get linear independent set V1 to Vk that still spans V. Okay. And now V1 to Vk is basis of V, so but it only has k vectors. So dimension of V is k, but we also know the dimension of V is n, and k not equal to n, so this is a contradiction. So what's important here is this process of getting a linearly independent set. Okay. Is we start with a set of vectors that are linearly dependent, then we can always get rid of them one by one until we get a linearly independent set. And if the starting set span the whole space, then the final set still span the whole space and it's linearly independent, so it's a basis. And yeah, I have an example. Here we have that. We have a 3 vector. We want to show whether it's a basis, and we see they have 3 vectors, and so we only need to show that they are linearly independent to show that this is a basis. So before we need to show they are linearly independent and they span, but here we use that is 3 of them, and it's linearly independent and it's already span everything. And to check the linear independence from the theorem we had today, we know that it's 3 vector for R3, then we only need to check the determinant, and determinant is not 0, so it's linearly independent, and it's a basis for R3. And once again, we are using the first one. So we have 3 vectors and they are independent, then it's already a basis. And I guess that's not go over time, but we have a theorem 3.4.4 that says that something about the basis of V. And I guess we'll continue next time for this theorem. And so here we have a lot of abstract proof, but hopefully they give you a good idea about dimension and the basis of vector space V. Okay. So we'll soon next Monday, and we should have a show homework about show homework about 3.3 and 3.4. Okay. So see you next Monday.等于0应该是说，就是只有0这个 vector 这样，就 null space 总是可以，这个应该要写得清楚一点。
它不是 set。
这是它 set， 所以但 null space 总是有一个 vector 嘛，就是0 vector，所以等于0，应该它应该要写清楚一点的话，应该是要说等于这个东西这样子。0就是说只有这个东西，然后不等于0就是有 non-trivial 的意思。Midterm, yeah. But I think I haven't decided yet, but I think there will be both. There should be proof and a calculation. Yeah.
More on proof.
I cannot say right now. But, yeah. Hopefully there will be good balance.